Hi all. The concept that we are going to see today is Warshall Transitive closure. Okay, so the Warshall Transitive closure is that it's a concept from dynamic programming. Okay, so Warshall Transitive closure. Before that, we learn what is dynamic programming. We all know what is dynamic programming is, right? The dynamic programming is nothing but a programming approach or a technique through which we can solve a problem. Okay, so we have many n number of problems in our hand, and this dynamic programming, one such technique to solve that problem. Okay, so before this dynamic programming, we have seen this greedy approach, and also we saw the brute force approach, right? So these are one kind of approaches or techniques which help to us to solve some problem. The similar way, the dynamic programming is also a problem through which is also a technique through which some problems like zero one knapsack and longest common subsequence, matrix chain multiplication, and Warshall transitive closure, Floyd all path shortest path. These kind of problems can be solved by using this dynamic programming approach. Okay, so the dynamic programming approach, the main aim of dynamic programming approach is how they will solve the problem is they'll divide a problem into sub problems. Okay, the problem will be divided into sub problems, and this the subproblems will be further divided into sub-subproblems, and the values of subproblems will be stored in a table called memorization table. Why we are using this table? Because it is used for when the subproblems values are stored inside the subproblem values are stored inside this table, and these values will be helping us to solve the main problem answer. That it will give you a picture of how to solve the main problem. Okay, by adding the solutions of sub problem, we can all compute the solution for main problem. And also it is and also we don't have to keep on finding the solution of, if the subproblem solutions are not stored in the table, then we will not know we will be then we will be keep on finding the solutions. Okay, so that it will take more time. So in order to avoid those things, the subproblems are divided into subproblem in order to reduce the complexity, and the solutions are stored in the table in order to reduce the time complexity for solving the problem. Okay, the subproblem solutions are added up together to find the solution of the main problem. So this is the way the dynamic programming will solve a problem. So today's class is about Warshall transitive closure. Okay, so the transitive closure by using dynamic programming technique. Okay. Mm, to find, so why we are going for this Warshall transitive closure is to find the existence of path between all pairs of vertices in a given weighted connected graph. Okay, so if there will be a graph. Okay, the graph, our aim is to find all the path between, okay, all the path directed or indirected path. Okay, direct or indirect path. Okay, we are not concentrating on only the direct path. If there is an indirect path that's existing, that is also found by using Warshall transitive closure. Okay, so it is applicable both directed and undirected graph. Usually you'll have a directed graph only. Okay, so if there is an undirected graph, then you can also you have to go in both the range. I'll tell you at the end how to solve for undirected graph. And to determine transitive closure of any graph, you have to find the adjacency matrix. Okay, so where this I'll tell you the steps one by one. Before that, we'll see what is the application of this Warshall transitive closure. So you can go for data flow and control for dependencies, redundancy checking, inheritance testing in object-oriented software. Okay, so fine. Okay, so if this is a graph, okay, so we have to find the path existed between. There is a direct path, okay, A to B, there is a direct path. But we also need, if there are, okay, so if there is a direct path between A to B, okay, no need to worry about it. Check for A to C, there is no direct path connected to A to C. But we have to find if there is any indirect path connected to A to C. Okay, for example, from A to B I can go, okay, and B to D I can go, and D to C will take me to C, right? So A to C there is no direct path, but I have a path through B, D, and C. So that is what is a Warshall algorithm. This helps us to find the path between any two vertices. Okay, so somehow it may, if there is no path it is not problem, but if there is a path then that will be found by using Warshall transitive closure dynamic programming approach. Okay, fine, let me take an example. Fine, so this is a graph that I have taken. Okay, so before talking about the graph, let me tell you the steps of how to solve the problem, how to solve this approach. Okay, steps. First you have to find adjacency matrix. Sorry. Okay, next step is if there is direct path existed. Okay, if there is a direct path existed, okay, put 1. Okay, if there is indirect path, okay, or you can also say if there is no path existed, then put it, mark it as 0. Okay, so first step is to create an adjacency matrix, and in that matrix if there is a direct path between two vertices then you have to put it as 1. If there is no direct path then you have to mark it as 0. Okay, then we have to, after finding that, okay, you have to add each vertex at a time. Okay, I'll tell you. Okay, add vertex at a time, add a vertex at a time. Okay, and just okay, add a vertex at a time. Okay, so do you, if you're adding a vertex, okay, leave that row and column. Okay, just I'll write the rules. While solving, we'll solve it very properly. Okay, so first we have to, so third step is you have to add vertex at the time. If you are taking a particular vertex, leave that vertex row and column. Okay, so fine, these are the steps. Okay, so let me solve from the first step. Okay, so the first step is I want to find the adjacency matrix, so I'm telling adjacency matrix as or not. Okay, so now I'm going to find the adjacency matrix R naught. Okay, so just here it is not a memorization table, or the values are not stored in the table, but it is in the form of matrix. Okay, it is also a kind of row and column table. Okay, how many vertices are there? A, B, C, D, E. So I'm making that as my row: A, B, C, D, and E. And fine, again A, B, C, D, E. Okay, general matrix structure. Okay, so now I want to find the adjacency matrix by making direct path. If there is a direct path, I want to make it as 1. If there is no path, then I have to make it as 0. Okay, so check A. Is there any path? No, so 0. A, B. Is there is any direct path? Yes, you have. So make it as 1. Okay. A to C. Is there is any path? No, 0. Next is A to D, there is a path, so it is 1. And A to E, there is no path, so it is 0. Okay, so wherever you find a direct path, put it as 1. If there is no path existed, you put it as 0. Similarly for BA. BA, there is no direct path, so it is 0. BB, there is no direct path, 0. Okay, C, there is no direct path. BD, there is no direct path. And BE, there is no direct path. So how I'm creating this matrix? From the given graph. Okay, this is my graph of vertices and it has 5 vertices. And CA, there is no path, 0. CB, yes, you have a path. C to B, you have a path. C to C, there is no path. C to D, you don't have a path, direct path. Okay, C to E, you don't have a path. Okay, next is D to A. D to A, don't have a path. D to B, no path. You have a path between D to C, no path between D to D, and D to E, you have a path. And for E to A, E to B, E to C, and E to D, and E to E. Okay, so this is the adjacency matrix I have created. How I filled this? By if there is a path existed, I marked as 1. If there is no direct path, then I marked as 0. It's very, very important. Okay, so I have done these 2 steps. Okay, now I have to find by adding a vertexes at a time. Okay, so what does it mean? So I have to find R naught. See, now I want to find R1. Okay, so how to find R1? So if okay, so okay, so how to find R1? Okay, so R1 is found by adding one vertex at a time. Okay, adding, now I'm going to add vertex A. Okay, so adding a vertex at a time. If you're adding a particular vertex, leave that vertex row and column. Okay, so I am going to create another matrix R1 by adding a vertex A1. Okay, I'll teach you. Okay, A, B, C, D, E. A, B, C, D, and E. Okay, so now I'm going to add A in between the vertices. Okay, I'm going to check whether that is a path existed. Okay, so it's a very simple thing. Okay, fine. So fine. Okay, so if I'm adding a vertices A, I'm going to leave that row and column. So which means I'm going to leave this A row, see A column and A row. Okay, I'm not going to check any vertices or anything in this row and column if that vertex is included. So I'm just adding it as such. I'm not going to change all that. So I'm going to write that row and column. Okay, so first step is you have created an adjacency matrix. From the adjacency matrix you have created, now we are going to add a vertex A and check whether there is a path existing or not. Okay, if there is a path existing, you are going to mark it as 1. If not, you are marking it as 0. So now how to find it? Okay, so the path existed is okay. So now I can find, okay, now I want to fill these boxes. Okay, if there is one already existing, you can fill that also. Okay, so see here, there is one, I'm filling it, and here there is one and one dealer. You have here one and here one. So why I'm doing this? Because I'm just checking if there is a, if I'm adding a path in between, if I'm adding a vertices in between, can I reach to another any other vertices through that path? Okay, so if already the vertex or this path is existed, I don't want to worry about it, right? So I'm just leaving it. Okay, so only if there's a path existed, I'm filling the path in the matrix table also, matrix also. Okay, so I'm not touching those things. So just I'm going to check where are the 0 part is there. Those part I'm adding a new vertex and I'm checking whether that is a path existed. I'll teach you. Okay, so now fine. So now this is the empty space where you have no path existed. So now I'm going to add A in between. Okay, so how to add? So I want to find the place. This position is called as B to B, right? So B to B. So now I'm going to find for B to B. So how to add? So now I'm going to add a vertex A in between. So if I add a vertex B in between, so my path will be B to A to A to B. Okay, so if the check whether there is a Okay, so in between you have to put and okay, normal truth table. Okay, and so check if the path, the place that I'm going to check whether the path existed is b to b. So by adding vertex in between a, I'm checking it. So b to a and a to b. Okay, so b to a and a to b. Okay, are you getting it? So in between I have added a vertex called A. So check whether B to A there is a vertex, there is a path. Okay, always check the previous created matrix. So this is the for this matrix, this is the previous created matrix. So for B to A, I'm checking a path. No, there is no path. And okay, A to B, there's a path. So according to the truth value of and what is this? What if there is any one has 0, then answer will be 0, right? So 0 0 1 0 0 0 0 is 0, 1 1 alone will be giving me 1. So when I added a between b to b, I'm not getting any path, so I'm marking it as 0. Sin. Okay. Now here again you have to check. You have to check for next value. What is that next value? That is b to c. B to c. So now I want to add a in between. B to a and a to c. Okay. So if I add this thing, what happens? Just okay. If I add this in a in between, so b to a, I'm checking a path. There is no path, and A to C. A to C, there is no path. So 0, 0 will be 0. So there is no path. Okay. Similarly, I have to calculate for every place where 0 is existing. Okay. So next is B to D. Okay. What is B to D? B to A and A to D. Okay, so if I add B to A, see if I check there is a path, no, there is no path. Then A to D, there is a path, but since it's an AND operator, there is no direct path. So the path is not created, even though if I add A into it. Okay, so the answer is 0 here. Similarly, B to E. So B to E na, B to A, E to, okay, next is B to E. So B to A and a to E. Okay. Since B to A there is no path, obviously you know the answer, there is no path. Okay. So next is C to C. Okay. So this path, this box to be filled. So B to C, C to C na, C to C na, C to A and A to C. Okay. So C to A there is no path. So you can blindly put there is no path. Okay. C to D. Similarly, if it is C to D, I want to add a new vertex called C to A and A to D. Okay, so C to A there is no path, so I can put it as 0. So fine. So even if I calculate every values one by one, I will have the same matrix as above. Okay, 0 1 triple 0 0 0 101. Okay, you can check with the answer that I got, 0 0 1 0 0. Okay, so this is the matrix that I got. Okay, so if I'm adding a vertex a in between, I'm not getting any new path. Okay, so now I'll create next matrix, because I should not stop it here, because I have just added a vertices a only. Okay, now I have to add other vertices. I have to do by adding all the vertices. I should not stop with a single vertex. I should add all the vertices in between, and I have to get the matrix, or I have to check whether there's a path is existed. Okay, now next is adding b. Now a is already visited. Okay, now we are going to add vertices b. Okay, okay, a vertices b. Okay, so if I'm adding vertices b, I should not include b row and b column. Okay, so I'm not including this row and this column for my calculation. Okay, so I'm just that it left untouched. Okay, so now I'm creating the matrix R2. Fine. So A, B, C, D, E. Okay, A, B, C, D, E. Okay, so now I'll add 1 0 1 0 0 as such, because that is now I'm going to add b row. Then 0, 0, everything is 0. Okay, now I'm going to fill the places where 1 is already available. 1, C வந்து கீழே 1 1. Okay, here you have one more 1. Okay, so I'm just going to check if I'm adding b, will I get any row or not. Okay, so the same value, same method, by adding. If I want to find a to a, I want to add b in between now. Okay, a to b and b to a. Okay, so check whether a to b there is a path, a to b there is a path, and b to a, check whether b to a has a path. No, so 1 and 0 will give me answer 0. So I want to fill it like this. Okay, so if I fill this, I'll get a matrix that is 0 1 0 1 0. Okay, 0 0, everything is 0, then 0 1 triple 0. Okay, and d will be 0 0 1 0 1, and 0 0, everything is 0. Okay, so the matrix will be unchanged matrix, you will not have the adjacency matrix will be repeated. And one more thing, whenever you are going to find the path from the previous matrix, not from the the first matrix you have created. Okay, for example, if I want to find a to a, I want to check the value, if there is a path existed between a to b or not. From the previous matrix, a to b there is a path existed, and b to a there is no path. Okay, so you have to check only the previous matrix, because this, suppose I have changed, when I add some vertex, I have might have created, or I might have got some vertices, the indirect path in between that. So I that is updated in the previous matrix table only, matrix only. Okay, this matrix is the one you have created initially, but that might have not updated with the new values. Okay, so please remember, whenever you are going to calculate the path existed between two graph, then you two vertices, then you have to use only the previous created matrices, not the one you have already created. Okay, not that one you have already created initially. Okay, so consider only, get only, check only the previous matrix. Okay, so now we got R2 matrix. Now I'll just, okay, fine. So my R2 is this. Now I'll, fine. So now my R2 is this. Now how I got this R2? By adding a new vertices B in between, I got this row, I got this, but I got this matrix. Okay, so here what you observed is, you will not have a change in R, not R1. Okay, R2 also. Okay, that is the adjacency matrix what you have created by adding from in the adjacent matrix, after adding vertex A, even after adding vertex A and vertex B in between, you didn't had any change in the rows and columns. Okay, so now we'll check for next matrix. So next matrix is by adding row vertices C, adding C. Okay, so for adding C, what is the vertices you will leave? You will leave this row, C row and C column, and I'm going to use this only to check whether there is a path existing or not. I'm not going to check, use this matrix or the initial created matrix. Okay, so now I'll create and show you. So this will be R3. Okay, so 0, sorry, A, B, C, D, E, A, B, C, D, E. Okay, so now so I'll leave this row. What is that row called? 0 0 0 0 and C column 0 0 0 1 1, and C column, C row will be 0 1 0 1 triple 0. Okay, so this row and column is left, along with wherever 1 is existed, I'm leaving that also. Okay, yeah. Okay, fine. Thank you. Okay, so these are, so I'm going to check the 0 part where any row is any part is existing, if I add C in between. So I'll check one by one. Okay, okay, so now for A to A. So if I add A to A, watch, if for the vertex A to A, okay, I'm checking by adding C. So A to C and C to A. Okay, what is A to, so check for the previous matrix, A to C, there is no path, and C to A, there is no path. So if I'm doing with AND operator, it will give me 0 only. Okay, next is A to E. A to E. Okay, so if I add C in between, so A to C, there is no A to A, sorry, this path, A to C, there is no path, and C to E, you have a path. C to E, okay, 0. So 0 0 will give me 0 again. So one trick is, if you know a first value you got as a 0, directly you can mark it as 0, because anything with 0 in AND operation will be giving 0 only. So whenever you encounter 0 at first, you can just directly put it as 0 in the matrix also. Okay, so B to A. So B to A, it is 0. So I don't want to check. Okay, then B to B is already 0. So I don't want to check. Okay, because B to B. So if I add C in between, okay, B to C will be 0, and C to B will be, C to B is 1. So even though you have 1 here, and operation 0 1 will give me 0 only. Okay, so only I'm just telling you. Okay, B to D, there is no direct path between B to D, so I'm putting it as 0. B to E, there is no direct path, so you can also use this step also. You can use this step one by one to find also if you're confused. Okay, so then D to A. Okay, so next is D to A. I'm going to check for D to A whether there is a path existing if I'm adding C in between. D to A. Okay, so the path in between is D to C. Okay, I'm checking whether D to C there is a path. D to C there is a path. Okay, and C to A. C to A, is there a path? No. So it will give me 0. Okay, D to C. Okay, D to A. Next is D to B. Okay, D to B, what is D to through C? Okay, so D to C, I'm checking where it's a path or not. Yes, you have a path. And C to B, you have a path or not. C to B, yes, you have a path. So what will be the answer? It will be 1 here. So first time you have changed, you have got a, and not a direct path, you have an indirect path. Okay, so the how I found it. So if I want to find D to B, okay, what I have done, I have to create a path through C. Okay, because I'm adding C vertex now. So D to C and C to B. So what is D to C from the previous matrix? D to C is 1. And okay, C to B. C to B is also 1. So 1 and 1 will give me 1. So I have not a direct path, but I have an indirect path between D to B by adding C. Okay, so let me show that. So D to C through, okay, D to B. Okay, so D to C, I am not, okay, D to B. Okay, from D to B, I don't have a direct path. Okay, see here, I don't have a direct path between D to B, but if I add C in between, I have a path. That is what it means. Okay, can you check it? So see here. Okay, so here D to B, I don't have a path, direct path. Okay, but if I add a vertex C in between, I have a path to B. So that is what it means. Okay, so this is what we are going to find in transitive closure. Okay, next is, okay, next is this part. Okay, D to D. Okay, D to D, I'm checking whether there is a path is existing. D to C, okay, and C to D. D to C, there is a path, yes, and C to D, is there is a path? No. So 1 and 0 will give me 0 only. Okay, okay, next is E to A. Okay, E to A, I'm checking whether there is a path existing or not. So E to C and C to A. Okay, so E to C is, what is the E to C? Previous matrix, E to C, there is a path, and check whether C to A there's a path. No. So 1 0 will be 0. Next is E to B. So E to C and C to B. What is E to C? Okay, check always the previous matrix. E to C will be 1. Okay, and C to B is 1. Okay, so 1 and 1 will give me 1. So that's a indirect path. Okay, so I'm putting it as 1. Okay, so E to B there is no direct path, but if I add C in between, I have a path. I'll show you. E to B there is no direct path. Okay, E to B there is no direct path, but if I add vertex C in between, I have a path to C B. Okay, that is what this adjacency matrix, sorry, this transitive closure help us to do. Okay, next. Okay, fine. So, okay, next is E to D. E to D. Okay, so E to C and C to D. What is E to C? E to C is 1. C to D is 0. Okay, so there is no path. Then E to E. Okay, E to C and C to E. What is E to C? 1 and C to E is 0. Okay, so 1 0 will be 0. So this is the adjacency matrix or the matrix that I have got after adding vertex C in between. Now I'll add vertex D in between. Okay, so we should not stop. Okay, we have to add all the vertices and check whether there is a path existing or not. Okay, now I'm adding adding D in between. So which matrix you have to check? You have to check only this matrix. Okay, so ignore the previously created matrix, check only the newly created matrix. Okay, so now if I'm adding D, what are the rows and columns I have to ignore? I have to ignore this D column and D row. Okay, so fine. So likewise you can remove, you can ignore this row and column as well. Wherever there is one presented, you just ignore that also. Okay, so what is the matrix is called R4. Okay, 1 2 3, sorry, A B C D and E. A B C D E. A, B, C, D, E. Okay, so I'm leaving D row and D column. So 1, 0, 0, 0, 0 is the column value. 0, 1, 1, 0, 1 is the row value. Along with this, I'm leaving the 1 value. Okay. Okay, so now I'm going to check whether I can add a D between to get a path between two vertices. So A to A, check only this value, A to A. Okay, so I'm adding D between, so A to D and D to A. A to D is there is a path. Okay, A to D, yes, I have a path. D to A, I don't have a path. So D A to, so it is not giving me any indirect path. Okay, similarly A to C, A to C. Okay, so A to D there's a path, D to C there's a path. Okay, so here you have got another path. Okay, so to fill this box I need to check A to C, A to D by adding D in between A to D and D to C. What is A to D? A to D is 1 and D to C is 1. 1 and 1 will give me 1. So my graph have changed again, my matrix have changed. Okay, similarly next path, next is A to E. Okay, A to E க்கு you have to find A to D and D to E. Okay, A to D value enna, what is the value of A to D? 1 and D to E there is no there is your value. Okay, 1 and 1 will give me 1. Again now you have got another new path. Okay, similarly if I try like this, my matrix will be, okay, just check the answer. Okay, my matrix will be 0 0 0 0 0 1 0 0 0. Next, okay, next is 0 1 1 0 0. Okay, so this is the path you this is the matrix you would have got. Okay, next is by adding one more last matrix by adding E. Okay, so adding E. So ignore the this matrix because now we are just going to concentrate on this matrix only. Okay, so now I'll add this adding. Fine. So adding E now. Okay, now you're going to add E. Okay, so I'm going to ignore. Okay, so if I'm going to add E, I'm going to ignore this column and this row. E row and E column is ignored. Okay, so now I'll create the matrix again. A, B, C, D, E and A, B, C, D, E. Okay, so I'm adding 1, 0, 0, 1, 0, 0, 1, 1, everything is 0. Yes. Okay, so now I'll just um, okay, so I'll also add this 1 1 values. Okay, 1 1 1 pro C lower 1 D lower 1 1. Okay, so now I'm going to check these places only. So if I check, if I now for checking A to A, okay, A to A, now I'll add E in between A to E and E to A. So how I'll check this value? A to E, okay, that is a path, and E to A, there is no path. So this will be give me 0. Even adding E between, I'm not having a direct path between A to A. That is what it is telling. Okay, because A to A, from the graph you would have found what is A to A. If there is self loop, if there is a self loop, it will show you have a path between A to A. So generally from the graph that I have given, there is no direct path. Okay, right. There is no self loop. So obviously your just it's a trick. You all know, if you have doing properly you would have done. There is no self loop, so all the diagonals will be 0. B to B will be 0, C to C will be 0. Even adding a path in between, it will give you a, it will not have a direct path, right? So Z. Next, similarly, if I fill this table, your matrix will be 0 0 0 0 double 1 0 0. Okay, so this will be your matrix. Okay, so unchanged matrix, there is no change from re sorry, the matrix value, this matrix is called, what is the value of this matrix? R5. Okay, so there is no change between R4 and R5. Okay, so this is the matrix you got. So what does what does this matrix teach? Because the matrix teach that if there is a path existing between A to B, there is a path existing between A to C. How? It is either directly connected or somehow it is indirectly connected. Okay, so that is what it is given. So here this one represents there is a path existing. Okay, path existing either directly or indirectly. That is what the meaning is. Got it? So likewise you have created the matrix where it says that whether there is a path existed or not. Okay, so since this is a direct graph, you have found it. Okay, if there is an if the it is an indirect graph, for example, if okay, I'll show you. For example, this is a direct graph. What is direct graph? You have a direction pointed, right? So if suppose a graph given with in without direction, A, B, C, D. Okay, if this is the graph without any direction, then how the adjacency matrix is created? A, B, C, D, A, B, C, D, because the first step is to create adjacency matrix R naught. Alright. So if there is A to A, there is no path because there is no self loop. A to B, you have a path. Okay. A to C, there is no direct path. A to D, you have a path. Okay, since there is no direction marked, you have to put one for both the ways. For example, A to B, there is a path. You should say that A to B has a path. Similarly, B to A is also having a path. Okay, so if there is a direct graph, you can mark according to the direction it is pointing. If you got an indirect graph, you should make this adjacency matrix pointing both the ends. Okay, A to B you have a path, B to A is also you also have a path. So likewise, you have to fill the table, adjust the matrix and find R naught from R naught to R1, R1 to R2. Likewise, you have to keep on finding the matrices. Okay, how to find those matrices? By adding each vertex at a time. So this is what a Warshall transitive closure. I hope you understood this class, and if you have doubts, you can ask me. Thank you all.